We present a partition-based framework for building and validating regression models. Our framework helps users to understand relationships between observed variables, called features, and a dependent quantitative target variable. Specifically, it allows finding the most useful features for explaining the target using a regression model. Also, existing regression models can be validated and visually compared using our framework. The framework consists of two interactive overviews: an overview of relationships between the target variable and every single feature, and an overview of relationships between the target and pairs of features, allowing users to analyze dependencies on pairwise interactions of features. Each overview provides a ranking of features or feature pairs according to the relevance for the target. Visualizations of the target over the domain of each feature show the qualitative structure of relationships. The sequence of the plots is determined by the relevance ranking, ensuring that the most relevant plots are displayed on top. This provides visual scalability for large numbers of features, and users can interactively change the ranking criterion in real time. A key aspect of our framework is that we partition each of the one- or two-dimensional feature subspaces into disjoint regions, and we aggregate all data items within each region. In 1D, the vertical axis of each plot is used to show percentiles and median of the target within each region. In 2D, the mean value or variance of the target is color-coded across the domain of the two features. The framework provides different partitioning and layouting modes, conveying different aspects of relationships, such as the shape, size, and significance of structures. In summary, the framework provides ranked visual overviews, focusing the user on potentially useful features first, while the structure of relationships is conveyed by the visualization. We are now going to demonstrate how the framework can be applied for interactive regression. The target variable is a measured consumption of natural gas, as needed for heating or cooking. The analyst wants to build a regression model to predict this consumption. The ranked overview of single features shows that the target is strongly related to the feature's temperature and day of year. The ranking in this example is computed by fitting a piecewise linear model for each feature and assessing its goodness of fit. To provide an intuition of frequency and stability of relationships, the goodness of fit is computed for different model complexities, increasing from left to right. In this case, temperature seems to be more stable than day of year, as it potentially explains the target even when using a low model complexity. Temperature is chosen as the first feature for regression. As the analyst wants to use a simple linear prediction model, but the visualization indicates a nonlinear relationship, squared and cubic occurrences of the temperature are used for fitting as well. The regression model is trained, and the residuals of the model are used as the new target, which updates all rankings and visualizations. The effect of the temperature is captured by the model. Its relevance for the target is reduced. The visualizations now show the local distribution of residuals across the domain of features. Structural patterns over features now indicate a systematic bias by not taking these features into account. Guided by these plots, another relevant feature is selected, making the prediction model two-dimensional. As additional features are considered in the model, more subtle effects emerge that were previously masked by other, more dominating effects, such as a dependency on the wind speed. It seems surprising that this highly structured dependency on the wind speed is not ranked to the top. Switching the layouting of regions to a frequency-preserving mode shows that the indicated trend is not very significant, as very few high wind speeds have been observed. Now, two-dimensional interactions of features are considered. The coloring of the plots shows the local prediction bias of the model. In other words, it shows a local tendency of over- or underestimating the target. Structural patterns in the coloring suggest systematic errors by not accounting for these effects correctly. The top-ranking interaction of temperature and day of year shows that the same temperature value can yield different consumptions depending on the period of the year. This indicates that an interaction of the two features should be included for accurate prediction. Another interaction pattern appears at high wind speeds and low temperatures. The analyst chooses to account for this wind chill factor and adds the 2D interaction to the model. The model is updated and the effect is captured. Further subtle relationships appear, such as an apparent dependency on the categorical feature day of week. During all model refinement steps, a quantitative model overview keeps track of the prediction improvement caused by each extension step. Users can perform backward steps and branch from the previous refinement if they are not satisfied with an extension. As soon as no substantial improvement can be achieved anymore, the user terminates the workflow, ending up with a multidimensional prediction model for the target. Linked views within our system can then be used for follow-up tasks to regression, such as a detailed validation using slices of the identified model.